Hi, and welcome to the SQL Challenge. I'm Kendra Little, SQLWorkbooks.com. In this SQL Challenge, your mission is to see if you can index a query and reduce the logical reads as much as possible. And we've got a couple different levels of solutions that you can attempt. The first thing to do is download and restore the database. I will be using the 1.3 release of the Babby Names sample database. It is a small backup that you download, unzip, and then restore to your instance. On my instance, I have an S drive that I'm restoring to. You may need to change your drive and folder locations, but my database is already restored. It should be pretty darn fast. I'm going to configure the database just in case I want to poke around in Query Store. I have enabled that, and I've also set my compat level on the database to 140. I am running a SQL Server 2017 Developer Edition instance here. Here's our challenge. For level 1 of the challenge, we have a query below this, and our challenge is to design the best disk-based row store non-clustered index possible to reduce logical reads. This query is already fast. In the real world, this probably isn't a query that would come up on our tuning radar. We're really using this as a small scale example to learn about index tuning and explore how some things that look straightforward in a query to index may not be so straightforward. So in this initial level 1 challenge, our goal is to reduce the logical reads as much as possible with a single non-clustered index and to not make other schema changes. When we get into the higher levels of the challenge, our mission will be still to minimize the number of logical reads, but we can use more advanced features like indexed views, computed columns, indexed computed columns, and maybe a filtered index to test out to see on those more advanced solutions. Before I get started here, I am going to go ahead and first use the sample database. I've restored this with the name Babby Names 2017. If you'd like to, you can change the restore script to just make it the Babby Names database. I currently have a couple of versions of the database on my instance, so I went ahead and put the year in the name. It has name data from 1880 through 2017 for babies born in the United States. That data comes from data.gov. I'm going to also, before I baseline the query, I am going to rebuild the clustered primary key of the table. This table has a clustered index that is also the primary key of the table. It is on the first name ID column. And as I get into some of the more advanced solutions on here, I'm going to reset it at some points and rebuild the index. So I'm just going to reset this before I get started. We're measuring logical reads, and when we baseline this first time we run the query, it is going to scan the clustered primary key of the table, and whether or not that table has fragmentation will impact the number of logical reads we get. So I kind of want to just make sure by doing this index rebuild, I'm saying, all right, I'm going to rebuild the index before establishing my baseline of what it takes to run this query if we have to scan the clustered primary key, because on the initial run of this query, I haven't created any non-clustered indexes for it yet. Our query is looking for one-year wonders. In the ref.firstName table, we have a first report year column and we have a last report year column. So for the table, ref.firstNames, it has one row for each unique first name. It doesn't know anything about gender. It just knows about first names. Each first name has a first name ID column that is the clustered primary key of the table. And we also know the first report year, the last report year, and the total name count for that name. Our query wants to know about names where the first report year is the same as the last report year and total name count is greater than 10. We are ordering by total name count descending, and we are returning the first name, the first report year, which is also the last report year. We are aliasing it as solo report year. And then we're also returning the name count. I am using setStatistics.io to tell SQL Server when I run a query, return information about how much I/O it did to my Messages tab. I go ahead and run the query. On this first run, I haven't enabled execution plans. and I get my data back. I get 281 rows of data back for this query. Looking at my messages tab against the ref.firstname table, it doesn't give me the schema, it just gives me the name. I can see that my baseline is 482 logical reads. If I want to look at the execution plan for this, I can turn on actual execution plans. Let's look at the actual. Now I'm going to see, for this baseline of my query, it should be scanning the clustered primary key. That's really the only choice it has. And sure enough, it is doing a clustered index scan against the ref.firstname table. It is sorting the data as well and then returning it. If I highlight over the clustered index scan, I can see there is a predicate. This is not a seek predicate. There's no word seek anywhere in there. This is a predicate, otherwise known as a hidden filter. We are scanning the clustered primary key, and for every row we are checking, is the total name count greater than 10, and is first report year equal to last report year? That's straight out of the where clause of our query. It is applying that as it scans through the index. It's like, okay, oh, do you meet my criteria? Do you meet my criteria? How about you? Do you meet my criteria? Your mission is, at the first level of this, your level 1 mission is to design the best disk-based non-clustered index. And if you get past level 1 fairly quickly, try your hands at level 2 and level 3, and I'll meet you back to see solutions and some samples on reducing the logical reads.